Hello, everyone. Welcome to the third MMMRN webinar. Today we have Muhammad Rubaid bin Shahadat Srishti Bhai with us. He'll be talking about his research titled A Molecular Dynamics Study of Heat Transfer Enhancement During Phase Change from a Nano-Engineered Solid Surface. So before his talk, let me introduce him a little bit. Uh, Srishti Bhai received his Bachelor of Science in Mechanical Engineering from Bangladesh University of Engineering and Technology in 2016. He received his Masters of Science from the same university in Mechanical Engineering in 2019. He worked as an assistant professor in Mechanical Engineering department at Haji Muhammad Danish Science and Technology University. He is currently pursuing his PhD at Michigan State University. During his undergrad and master's, he worked on nanoscale heat transfer and nanomaterials. At the Michigan State University, he's working as a graduate teaching assistant and is working in the heat transfer and fluid mechanics lab. He's also working in the CFD lab as a graduate research assistant, and his research focuses on the turbulent mixing enhancement in supersonic flow and shock turbulent interaction. Muhammad Rubaid bin Shahadat published 6 peer-reviewed journals, 9 conference proceedings. He is also a reviewer of 2021 AIAA Aviation Forum and Exposition held at Washington, D.C. He's also a reviewer of Journal of Fluid Engineering published by LSME. So I guess it's a very good opportunity for us to learn about his work and to know more about heat transfer phenomena. I guess heat transfer as a topic, as a research topic, has been studied for more than hundreds of years, but still, I guess a lot of a lot of phenomena associated with it are still unclear, and probably it will be a great learning opportunity for us from Srishti Bhai. So I guess without further ado, let me introduce him. So sorry, I mean, let me welcome him for his talk. So Srishti Bhai, so if you may start the talk. Yeah.
Okay. Thank you, Knight, for your nice introduction and invitation. This is Mohammad Rubaid bin Shahadat. Right now, I'm working as a PhD student in the Department of Mechanical Engineering at Michigan State University. So at first, I would like to thank MMMRN for inviting me as a speaker to this webinar. And while I was a student at undergrad at BUET, I used to take help from different members of this group, especially from Satyajit sir and Saurav sir in my research. So I'd like to thank the current president, vice president, all the members of this group, and all the members who are connected to this webinar. So I'm starting. Today I'm going to present one of our published work recently in MDPI Process Journal. The name of the paper is A Molecular Dynamic Study of Heat Transfer Enhancement During Phase Change from a nano-engineered solid surface. I chose this topic because some part of the work I did when I was an undergrad student back in BUET. So I chose these topics because most of our audience are from undergrad, and they might have an idea what they can choose for their research topics in their 4.1 or different projects they can work on. So this is our learning objective. So as molecular dynamic simulation might be new to someone, so I will start from the basic, what is molecular dynamic simulation. Then I will talk about some key features. Then I will talk about the very important potential that is called the Lennard potential. Then I will move to my work and talk about what are the surface modification used in our work, and then benefit of those surface modification in phase change phenomena. So we all know that nanoscale phase transition is very important nowadays in electronic cooling of devices, energy storage devices, different type of surgery, especially the laser surgeries, and different type of cleaning like laser stream cleaning technology. And sometimes in different application, we might need to enhance the heat transfer from a specified surface, and nano-level surface modification might be very helpful in those cases. A lot of work has been published in this field, but most of the work was based on changing the surface texture and like from hydrophobic to hydrophilic condition, and adding some of the nano-level surface, nano-level structure on the surface. But a very less work has been done on nanoslot and nano-level surface roughnesses, and also on the active nucleation side. That's why we focused on this side. So this paper is basically a compilation of some of the previous work and some of the present work, so that it will be very helpful for future researcher to go through one single paper and have an overall idea. So these are the surface modification we have used. So on the flat surface, so we have a flat surface, then what we did, we basically changed the surface weighting condition from hydrophobic to hydrophilic condition. Then we have implemented some of the nanostructures on the smooth surface. Then we have cutted some of the nanoslot from the smooth surface. And then we have introduced some of the nano-level surface roughnesses on the smooth surface. These are the 4 types of surface modification we have done in this paper. So the MD simulation, I'm starting from some theoretical concept, and then I will come back to our paper. So most of the simulation we did in our observable real world are some of the large scale or macro level simulation, but molecular simulation is basically work with the 2 small things that are not directly observable in our naked eyes or something like that. So basically they work with the MD simulation work with the atoms and molecules, different types of atom and molecules. So at first the atoms and molecules are allowed to interact at a certain fixed time. Then we calculate the trajectory or the location by directly from the Newton's law, and the force calculate we from interatomic potentials. And the MD simulation concept is also different from our continuum hypothesis. So in our continuum hypothesis, we treat the fluid as a bulk. So say, for example, we have a fluid flow in a certain pipe. So when we have a fluid flow in a certain pipe, then we can say that this fluid is work as a whole bulk system, right? From the continuum hypothesis. That means if we go at a certain point, we might have the fluid particle there. And also we can calculate the properties from that point of that whole fluid. But MD simulation concept is kind of different from this continuum hypothesis. We can't treat fluid as a bulk system or bulk. We have to work with the discrete particles. So when there is a fluid flow in a pipe, if we go at a certain point, we can't surely say that there is a particle there. There might be a particle, there might be a void. We might reach at the bond of this between the 2 particles, whatever it is, but we can't say that this fluid is working as a bulk system. And also for different boundary condition, for continuum hypothesis, we normally use the no-slip boundary condition at the wall. For MD simulation, not all the time we can use that kind of boundary conditions. So these are some basic differences between MD simulation and our continuum hypothesis system. Then when we are using with the atoms and molecules, why are we not using the quantum mechanics? If we use the quantum mechanics and solve the wave equation, then it would be the most accurate thing, but it is really hard to program and solve the wave equation, and it will take a lot of computing power. That's why we avoid this quantum mechanical system. Rather than we go to our classical mechanics, that is Newtonian mechanics in the system. And when we go to this simplification, there might be some less accuracy, but we make these things doable by using this classical Newtonian mechanics. So these are some basic things about the MD simulation. And how this simulation works. Basically, for each and every particle, we have to find out the position, the momentum, charge, and the bond information. Bond information means what kind of bond it is, and what is the bond length, and all other informations. So between 2 particles, we basically calculate the force directly from the Newtonian mechanics, as I already mentioned, that is F equal to ma. Then we basically again work with the force equal to negative gradient of the potential energy function. So we have the force here and force here, then we equate these 2 equations, then we'll find the acceleration from this. So when we have the acceleration, we might calculate the location and velocity and all other information. So this is a very basic type of algorithm we used in MD simulation. So at first, we basically work with the initial position, initial velocity at initial time. Then we go to the predictor step, and the predictor step, we basically calculate the roughly the location of the velocity. Then we go to these steps and calculate the acceleration from here. Then we basically go to the predictor step and correct this equation. That means that step is called the corrector step. So at the corrector step, we have the better and updated location of velocity. Then we basically apply different boundary conditions, temperature and pressure control technique here. Then we go to next time step, next iteration, and repeat all the procedures here. So this is the basic algorithm how MD simulation works. This is a very important potential I'm talking about. So this is called the Lennard zone potential. So then for LJ potential, say for example, we have two different atoms and the atoms are at an infinite distance. So infinite distance means there is no interaction in between those two atoms. Now we are making the atom to come closer. So when we are making the atom to come closer, then there will be some attraction force working in between that two atoms. And when we're making them come closer, more closer, then the attraction will enhance and it will reach to an equilibrium position at a certain location. And then if we make them more closer, then repulsive force will be dominant and repulsive force will start to work. So at first there is no interaction, then there will be some attraction, then there will be repulsion. So that's the basic thing here. So we can show it from this graph. So these are two atoms separated by r distance. When the r is very high, there is no interaction there. But when we're making them closer, then the interaction starts to work and the potential energy goes lower. So these are the interaction zone and it will come to an equilibrium position. And then when we make them more closer, then the repulsion force starts to work and the potential will go up. So all these phenomena can be described by this equation that is called the LJ potential equation, which is this equation is very important here. And there are different terms there. I'm just talking about those terms. So this R is basically the separating distance between those two atoms. I have already mentioned that is the R. Sigma is basically called the length scale. So sigma is basically length scale. That means that it is a distance where the interaction will be zero. And epsilon is called the depth of the potential, or sometimes it is called the intensity of the potential. So that is called the epsilon. And this power 12 works for the repulsive one, and this power works for the attraction one. So sometimes this equation is called 12-6 LJ potential equation because of this power. So these are the theoretical concepts we need to know for our study. Then I'm going to our simulation methodology. So this is our simulation domain. So we can see that there are three distinct domains here. So this is the solid wall. This solid wall is made of copper. There are a few layers of copper atom here. Then this is the liquid layer, and this is liquid argon, and these are the argon vapor. So there are three distinct zones: solid wall made of copper, liquid zone made of liquid argon, and vapor zone made of argon vapor. And these are the four types of surface modification we have used here. So first type of surface modification, this is completely a flat surface, but we will change the surface condition from hydrophobic to hydrophilic. Then this is a surface with nanostructures. As you can see that there are nanostructures has been put on this solid surface. There are 4 nanostructures here. This is cutting the nanoslot from the surface. There are 3 nanoslot we have cut it from the surface. And this is the nano-level surface roughnesses. So these are the surface roughnesses we have added here. And I have changed the viewing angle to make it more clear, the roughnesses here. And I have already mentioned, I have used this LJ potential model here. Now we have used a cutoff theory here that is called cutoff radius. We have selected 3.5 sigma argon of argon. So what is cutoff radius and why do we need this cutoff radius? So for example, we have 100 atoms. So if we pick a single atom, then this atom should have interaction with the rest of 99 atoms, right? So if we work like that, the single atom will interact with all the atom inside the domain, then it will be very computationally costly. That's why we basically select a certain radius. So that radius works like that. So within this radius, the atom will interact with each other, but outside that radius, that atom will not interact. That means this equation will work when our distance is less than the cutoff distance. But when we'll go to higher than the cutoff distance, then we won't work with any potential. So that would be 0. Okay. And these are the values we have set. So here we have two different type of atom, that is copper and argon. So there should be 3 type of potential. So potential in between argon and argon, potential in between copper and copper, potential in between argon and copper. So these are the values we have used in this simulation, and these values we have taken from some of the previous study and some of the books. The time step we have used in this simulation was 5 femtosecond. And we have used the periodic boundary condition and X and Z direction and fixed boundary condition in Y direction. That means if we go here, so in Y direction, that is the fixed boundary condition, and in rest of the two axes, we have the periodic boundary condition. Then we start with 90 Kelvin temperature, which is lower than the phase change temperature, basically, so evaporation temperature. So at first we keep 90 Kelvin temperature for the solid wall that is made of copper, and run the simulation for 0.5 nanosecond. Then we stop the thermostat and then try to equilibrium the system for another 0.5 nanosecond. That means up to 1 nanosecond, the temperature of the wall was 90 Kelvin. Then at exactly 1 nanosecond, we jump the temperature to 140 Kelvin temperature, which is more than the phase transition temperature or the evaporation temperature. So when we go jump to 140 Kelvin temperature, then the phase change phenomena will take place. And then we will run the system for more 5 nanoseconds. So if you go with there, you can see that these are the different surface condition: hydrophobic, hydrophilic, surface is nanostructure, nanoslot, and rough surface. And we can see that up to 1 nanosecond, the system temperature, wall temperature was 90 Kelvin. Then exactly at 1 nanosecond, we jump the temperature to 140 Kelvin. And then we allowed to run the simulation for more 5 nanosecond. Okay. So this is how we did the simulation. And there might be a question, why did we choose this 140 Kelvin temperature? So we choose this 140 Kelvin temperature, which is above the phase change temperature, that is the evaporation temperature. But this temperature is below the explosive boiling temperature. So this is very important because we don't want to go to the explosive boiling regime in this paper. That's why we kept the temperature lower than 173 Kelvin, because we found that the explosive boiling temperature of argon on copper plate is exactly 173 Kelvin temperature. So we didn't want to go to that regime. That's why we kept the temperature below 173. This simulation can be done at 130 Kelvin or 150 Kelvin, but we didn't want to reach to 173 Kelvin temperature. So I'm just talking about a little bit about what is explosive boiling temperature. So when the surface temperature is too high, then this is the liquid layer. So at the very lower layer of the liquid get evaporated, and when it goes to evaporative position, then the density will drop, and then this low density vapor will push the upward liquid to the upward direction. So a chunk of liquid will detach from this surface and go in the upward direction. So that is called the explosive boiling phenomena and explosive condition. We didn't want to go there, and that's why we kept the temperature lower than 173 Kelvin temperature. So here I'm just showing my OV2 screen so that I can show how the explosive boiling phenomena works. So you can see that here, a chunk of liquid is detached from the surface and go the upward direction. So this is called the explosive boiling phenomena. So this is the current project we're working on. So we basically avoided this region, and that's why we kept the temperature lower than 173 Kelvin temperature. And while the simulation we have done in LAMPS, and the visualization we have done in OV2. These are very common softwares, those who are working in MD simulations. So I'm going directly to my result and discussion segment. So at first, I'll talk about the surface wetting condition when we change the surface wetting condition from the hydrophobic to hydrophilic condition. So what is hydrophobic and hydrophilic surface? So when we have the hydrophobic surface, the contact angle will be more than 90 degrees. So this is a hydrophobic surface, and we can see that the contact angle of this liquid and this surface is more than 90 degrees. But when we'll go to hydrophilic condition, then the contact angle will be less than 90 degrees. Okay, so I'll go with the traditional definition. So hydrophobic means that is the water fearing. That means this fluid will not interact with this surface. So when this fluid will not have a good interaction with this surface, then it will not take that much heat from this surface. So the heat transfer will be lower for hydrophobic condition. But when we'll go to hydrophilic, that means the water loving condition. That means this fluid will interact more with this solid surface, and when there will be more interaction, there will be more heat transfer from this surface to that corresponding liquid. So when we'll go from hydrophobic to hydrophilic condition, we will enhance the heat transfer phenomena. Now we'll see the effect of heat transfer here. So this is the direction of increasing surface wettability. So at first, the surface wettability factor is 0.1, and that is called the hydrophobic condition. Then we have increased it to 1, that is called the hydrophilic condition. Okay. So when we'll go from the hydrophobic to hydrophilic condition, we can see that the liquid layer has been decreased. The liquid layer has been decreased means more atom has gone to the vapor phase. That means when we'll go from the hydrophobic to hydrophilic condition, we will do a better enhancement in the phase change phenomena. So same thing we can see from our temperature profile. So this is a temperature profile. These are the different surface wetting factor. So just focus on 0.1 and 1. 0.1 means the hydrophobic condition, 1 means the hydrophilic condition. So when we have the hydrophobic condition, we can see that the temperature buildup is not that high like the hydrophilic condition. So when the temperature buildup is not high, that means heat transfer will not increase, and phase change phenomena will not be that good for the hydrophobic condition. So this is the first surface modification. Changing the surface from hydrophobic to hydrophilic, we can enhance the heat transfer phenomena, and certainly we can make the phase transition a lot faster. Same thing we can see from the net evaporation number. So net evaporation number is basically changing the number of vapor particles after a certain time. So we basically run the simulation and calculated after a fixed time step the number of changing of vapor atom inside this domain, and plotted this graph. So this is called the net evaporation number. And from the net evaporation number curve, we can see that the slope of the hydrophilic condition is higher than the hydrophobic condition. So this is hydrophobic, this one is hydrophilic. So the slope is higher means the evaporation takes place a lot faster rate. Evaporation takes place at a lot faster rate means it is the phase change phenomena has been enhanced. So the same thing we saw from the temperature profile, the temperature is enhanced, phase change phenomena is enhanced when we go from the hydrophobic to hydrophilic condition. So that's how we can enhance the heat transfer from flat surface. So that is our first surface modification. Then this is our second surface modification, that is called introducing the nanostructures at the surface. And we can see that we have introduced 4 nanostructures. 2 are here and 2 are in this direction. So there are 4 nanostructures here. And when we have introduced 4 nanostructures, it has enhanced the surface area to 43 0.36 nanometer square. So we know that heat transfer is directly proportional to the effective surface area. So when we have increased the surface area, we will definitely increase the heat transfer from that surface. So by introducing this nanostructure, we can enhance the heat transfer. Same thing we can see from the temperature profile. So this is the temperature profile for surface with nanostructure, which is higher than the flat surface. That means temperature has built up more and the heat transfer will be more for surface with nanostructures. And same type of thing we can see from the net evaporation number curve. The slope of this line with surface with nanostructures is higher than the flat surface. That means heat transfer has increased there, and a lot more particles has gone to the vapor phase when we go to the surface with nanostructures. That means it enhances the phase change phenomena. So this is our second type of surface modification. By introducing nanostructures, we can enhance our heat transfer from any solid surface. So that is the third kind of surface modification, that is introducing nanoslot. So for nanoslot, we have cut nanoslot here. We have seen that there are three different slots are cut from the flat surface. And when we cut the nanoslot, we basically enhance the surface area by 63 nanometer square. So we can see that the liquid layer thickness is lower here. That means more liquid has gone to the vapor phase. That means heat transfer phenomena and phase change phenomena has been enhanced by introducing the nanoslots. And we can certainly see it from our temperature domain, temperature profile of the domain. So when we have the nanoslot, we have the higher temperature than the flat surface. That means heat transfer has been enhanced when we have introduced the nanoslot here. And same thing we can see from the net evaporation number curve. So the slope of this line with nanoslot is higher than the slope of this flat surface line. That means phase transition has been enhanced and evaporation takes a quicker rate when we have introduced the nanoslot. So this was our third surface modification. By introducing nanoslot, we can certainly enhance our heat transfer. And this is the introduction of nano-level surface roughnesses to the solid surface. So how we introduce this type of surface roughnesses? We basically deleted some of the atoms from the surface and created some of the hemispherical spaces on the surface, and that's how we created this nano-level surface roughnesses. And when we have created surface roughnesses, we totally changed the surface texture and morphology of the surface, and we basically enhanced the total surface area for heat transfer, and that's why the heat transfer will enhance for when we will increase surface roughness on the flat surface. So we can see from the temperature profile that when we have the rough surface, the temperature buildup is higher from the flat surface. That means heat transfer is enhanced when we have increased the rough surface here. Same thing we can see from the net evaporation number curve. So the slope of this line is higher than the slope of the flat surface line. That means the phase transition takes place at a quicker rate when we are using the rough surface. So that's the fourth type of surface modification with which we can enhance the heat transfer from a solid surface. Now, the previous fourth type of surface modification was our main focus was to enhance the effective surface area. So all the three cases, we have enhanced the surface area, and one cases we have changed the surface condition. Now, if we have the same effective surface area, but we are using different number of nanostructures, then what will happen? So this is a very small part of our work where we have the same effective surface area, but amount of nanostructure is different. So this is one nanostructure, this is two nanostructure here, but the surface area is exactly the same for both of the cases. Then when we'll have the surface area exactly the same, and we know that heat transfer is directly proportional to the effective surface area, when we keep the surface area same, then we can see from the density profile that the density is almost the same, density peak is almost the same for these two nanostructures. And if we go with the net evaporation number curve, we can see that when we have two nanostructure, the slope is slightly higher than the single nanostructures, slightly higher. That means though we can keep, if we keep the effective surface area the same, but we enhance the active nucleation site, heat transfer can be slightly modified, not that much. This is not a very effective way, but still we can slightly enhance our heat transfer phase change phenomena slightly, not that much, basically a very small amount of we can enhance by introducing this higher level of active nucleation sites. So these are the conclusions. So when we enhance the surface wettability conditions, change the surface wettability condition from hydrophobic to hydrophilic, we can enhance the heat transfer during our phase change phenomena. Then when we introduce any type of nanostructure, nano-slot and nano-level surface roughnesses, we basically can enhance heat transfer during phase change phenomena. And if we keep the effective surface area the same, it should not be an effective way to enhance the heat transfer during phase change phenomena. Still, we can slightly modify the heat transfer phenomena by increasing the number of active nucleation sites. So these are future modification. Right now, we didn't work with different type of size and shape effects. So the nanostructure size is just like a cubic nanostructure, but we can certainly change the shape and size of those nanostructure, height of this nanostructure, and see how it affects the heat transfer phenomena during the phase change. This might we might work with this project later. And also we didn't see the effects, these effects on explosive boiling temperature. So right now we are working below the explosive boiling temperature regime, but we can certainly go to the explosive boiling regime and work the same things and see the effect on exact explosive boiling temperature. So right now the explosive boiling temperature is 73 Kelvin, but we can certainly work with these procedures or this simulation and check whether that temperature is 173 Kelvin, or it enhances or decreases. So we might work with that thing also. These are the references used here. Okay, I'm finishing with a very popular quote: "Life is a relationship between molecules." So these are just molecules, nothing more. Thank you so much. Please, any question?
Thanks a lot, Srishti, for this great talk. It was a very enjoyable talk, and it was very interesting. So for the Q&A question, Q&A stage, if anyone has any question, you can ask it in the chat box. And also, if you have any question, you can unmute yourself and ask the question. That is also okay. So before we go to audience question, I had a small question. So
Yes.
if you can go to slide 12, I guess.
Yes. 12.
Yes.
This one, yeah.
Yeah, this one. So here you changed the wettability condition, and you talked about the weighting factor as different for hydrophobic and hydrophilic case. So my
Yes.
question was that how did you model this weighting factor in your MD simulation?
Okay, good question. That's a really good question. Basically, it is dependent upon if I go to this slide. So you can see that there is epsilon, that is interaction between two atoms, right? So basically, we change the interaction between the argon and copper level. So when you have a very low level of interaction, that means the surface is hydrophobic condition. Okay, but when you are going to higher level of interaction between this argon and copper, that means if you change the value of epsilon, the interaction value will increase, and you can certainly move from the hydrophobic condition to hydrophilic condition. So we basically change this value of epsilon in between argon and copper from lower value to higher value, and that's how we basically changed our wettability condition from hydrophobic to hydrophilic. And
So
there is a, yeah, please go ahead. Yeah.
Yeah, so this weighting factor, is it a multiplier of the
Yeah,
interaction?
there is a rule that is called Bishop mixing rule, and the equation is root over epsilon of argon into epsilon of copper. So that's the interaction between argon and copper. So we basically changed the multiplication of these two value under this root. So when the value is very small, then it is basically hydrophobic condition. But when we'll increase the value, then we'll go to hydrophilic condition.
I see, I see. So my follow-up question would be,
Yeah.
so I understand that, yeah, you're changing the adhesion and also the van der Waals interaction between the materials, and
Yeah.
that would change the weightability for sure. So maybe my next question is maybe more on the physical side. Maybe from a practical point of view, you have the same copper and argon,
Yes.
but you're still able to change the interaction between them, making the surface from hydrophobic to hydrophilic. So how would that be? I mean, how do you envision
Envision in the
physical
practical
phenomena?
systems, right?
Right, right. So that
So
corresponds to such
yeah, that's
difference in the
that's
way.
a really good question. So for our simulation, we have the flexibility to change that one, but when we'll go to like the practical phenomena, we might not change this interaction value directly by changing some values, right? So what
Yeah,
we can do, we can certainly work with different type of coating. So when you have a certain type of non-sticky coating, right? We were using. So non-sticky means the interaction is really low. Again, when we use the raincoat or that kind of surface, that raincoat surface is not really hydrophilic. That is basically the hydrophobic surface. So if we want to practically implement that one, we might work with different type of coating, and that coating will change from hydrophobic to hydrophilic condition. So, and that will be the effect of changing the surface condition from hydrophobic to hydrophilic
I see.
in the
So
practical phenomena.
yeah, so then you'll have a different material than copper, right?
Yeah,
The
exactly.
coating
So there might be a different coating material
right.
than copper. Yes.
Yeah, yeah. Okay, that's good.
Yeah.
And
Thank you.
also I
Thanks for
have
question.
one another small
Yeah.
question.
Yeah.
So
Sure.
that's so for I forgot the slide, maybe 13 or yeah. So
Okay.
you measured the effective surface area and yeah, this one,
Okay.
the previous one.
The previous one. Yeah.
Yeah, this one. Oh
Okay.
yeah, it's the same size. Okay.
Yeah.
So I had another question about that. So you said here this is the weightability factor, right? Oh yeah. So here you are changing the weighting factor, and the temperature seems to have different slopes for different weighting factor.
Mhm.
But my question is, for the weighting factor 0.1, for this small weighting factor, you have a linear change of the temperature. But then for the other factors, you have non-linear change. You are suddenly increasing, and then maybe it goes to a saturated value. So is there
Mhm.
any physical reason behind such non-linear development?
Uh, no, right now I don't have that one because we need to go for a different study. So if we want to see why this linear change is happening for hydrophobic condition, we didn't study, or we don't have any exact physical explanation for this temperature buildup so differently from these surfaces. Right now I don't have any correct physical explanation of that one. But yeah, I will definitely see that one, and if I get anything, I will definitely send you the explanation. Yeah.
Thank you so
Thank you
much,
so much.
Bhaiya.
Thank you.
I guess,
Yeah.
yeah, I have no more questions. So uh, I think Khan Mohammed Rabi Bhai asked a question in the chat.
Okay.
So
Yeah.
um, I can read it out loud, but Rabi Bhai, can you ask the question, unmute yourself and ask the question? I guess that would be more interactive. Um, and also you can
Sure.
explain the question.
Yeah. Thanks, Christy, for the talk. It was a very
Thank you.
good one. I actually learned a lot because I do not have background in the atomistic simulations. So I was basically wondering about, but what you're trying to accomplish here, we do it experimentally in our lab.
Mhm.
So we actually introduce like at different scales of pillars in different substrates. Then we actually look at the weighting velocity, like the initial velocity and all that, and how we can design better systems that is reliable, because that's one of the concerns. Because so I was wondering, what is your what's the driving factor for you when you selected a particular geometry for your nanostructures? For example, you used the nanopillars, I suppose, right? With
yeah, kind of, yeah,
yeah,
nanopillars, but
yeah,
it's like a cubic one, not a
right,
circular one. Yeah.
right. So I was wondering, like, what's the motivation behind this? So that would be my first question. Then
Okay.
I'll definitely follow up with the next ones. I have some couple of other questions as well.
Okay, sure. So basically, we started with a very basic type of geometry. So we didn't choose this particular geometry based on different studies. We basically started with very basic geometry, but right now we are working with different size and shape of this geometry that that one you have asked. And I have already mentioned in our future modification of this code is that we will basically work with different size, shape of the geometry and see what is the effect of those things. So right now it's just basically introducing structure there and enhancing the heat transfer. So that was the basic motivation. So when we introduce any structure, then it will enhance the heat transfer. That was the motivation. That's why in this paper we didn't work with the size and shape effect or geometry effect, but certainly we have the plan to work with the geometry effect in later time, like different type of nanopillar, or changing the height of the nanopillars, or some of the conical shape we might add here and see what is the heat transfer enhancement or how it will change like that. And thank you, Rabbi, for this nice question.
Yeah, no worries. I mean, so you're saying that the whole motivation was changing or increasing the effective surface area. So I was also wondering about how the heat transfer rate actually, I'd say, relates to the effective surface area. Is it linearly proportional? Because we say it based on the Newton's law of cooling, but I believe it's not that. Newton's law of cooling is not valid at the nanoscales.
Yes.
So how do you scale that? Yeah.
So it's not exactly the linear variation, or exactly not like the Newton's law of cooling. It's just basically when you will enhance the number of particle or effective surface area, it will just enhance the heat transfer, but it is not following exactly the same equation like the Newton's law of cooling. So there should be a certain relationship between this changing of area and heat transfer. So we haven't quantified that one in this paper. So if we want to work with that quantification, we have to change a lot of variation of different surface area, and then change the heat transfer, and then find out a correlation between this changing of heat surface area and the heat transfer from those surfaces. So we didn't work on these topics here, but definitely it will not follow the Newton's law of cooling, because that is not exactly applicable for this atomistic simulation. But we can certainly say that it will increase, but not exactly same format with the Newton's law of cooling.
Right. Oh, thanks for the answer. I mean, I have one follow-up questions.
Yes, sure.
So, I think the question was asked, like it was touched a little bit, but I would say, so the hydrophobicity or hydrophilicity of a particular surface, I mean, it depends on the surface energy, right? Right at the solid liquid interface.
Exactly.
So you are putting that. You already discussed the technique that you use to incorporate that in your code. But I also seen in different literatures that the geometry itself or the nanostructures itself on a particular substrate can actually hydrophilic and hydrophobic. So how did you? So it's although you're putting a different weighting factor in your code, but in reality, probably your geometry, because of a particular nanostructures or nanopillar height or spacing, it's not hydrophilic anymore. So I was
Okay.
wondering how would you distinguish between these two?
So your question is when I'm introducing the nanostructures on this solid surface,
Right.
whether that nanostructures is particularly hydrophilic or hydrophobic, right?
Uh, uh, like not really. I mean, just putting any structures on any surface, it changes
Yes.
the surface and the total surface energy of a particular surface.
Oh, okay, okay, yes,
Yeah.
yes.
So it can be. So that's how experimentally people have been doing, right? So they are
Right.
putting different coatings. They are putting different nanostructures, microstructures to make their substrate either hydrophilic or hydrophobic, or even in some cases super hydrophobic and hydrophilic.
Super hydrophilic, yes, yes.
Right. So I was wondering the geometry that you have chose. How do you make sure that it gives you a like a compliant weighting factor as you're putting in your code?
Oh, okay. So right now, when I put any nanostructures on this flat surface, then I basically worked with. So I didn't work with that thing when when you will give any nano coating or any nanostructures, you will definitely change the surface morphology and surface weighting condition. But that particular thing is not focused here. What we did when we used epsilon value, that is the interaction value here in this surface, we tried to use the same interaction value on this nanostructure. So when we are using the argon and copper interaction, I use the same interaction for this nanostructure and this flat surface, which might be changed when we'll use it in the experimental thing, because experimentally we can't exactly fix these things. Basically, it will change based on the surface, but at the simulation we can exactly fix these values and work with that one. So that's why I didn't change any epsilon value for this argon and copper when I introduced the nanostructures on this surface. So when I used nanostructure, it has the same type of weighting factor as the base surface. But in a different paper, I published it previously. On that paper, I basically worked on hydrophobic surface. I basically put some nanostructures that are hydrophilic, and that basically changed the whole story. So that one I worked in a different paper, but not in this one, not here right now.
Cool. Thank you. Thank you.
Thank you. Thank you so much.
So I have a few questions based
Yes.
on the discussions and everything. First of all, congratulations on your work, and it's a very good
Thank
work.
you. Thank you.
So I had a few questions, and some of those were already asked, and Rabbi touched on some of the things. So I'll just keep it simple. So first question is that, have you made any experimental verification of what kind of results you are having? I mean, not in terms of numbers, but at least in terms of trends. Like, are they giving the same trends or not, or similar experiments? Have you compared?
No, I haven't compared any experimental thing in this paper.
So one
but yes, but
No.
I basically search for some of the experimental papers, and they have the kind of similar trend, but not exactly numerically. But for trend, the trend might be the similar one. Like when we put the nano coating, I have some paper with nano coatings, and by changing the nano coating, it basically changed the surface structure, and it basically enhances the heat transfer phenomena from that surface. So right now we are not using coating, but we are changing the surface morphology from hydrophobic to hydrophilic. But we're having the similar trend, not exactly numerically, but from trend they're giving the similar thing.
Yeah, that's fine. I mean,
Yeah.
so you have chosen, like, I have seen some papers on this type of thing, and I'm not a fluid mechanician, but in such cases of applying MD on fluid mechanics problem, like, the fluid mechanicians prefer to choose a fluid which is very ideal, right? Like
Okay.
argon,
Yes. Yeah.
surface. So there's a so from what I observed, there is a reason for that,
Mhm.
because it's so what you are trying to see is that what is the engineering application, right? So how
Right.
it might change, but
Yes.
basically we are not even there, right?
Yes.
Because the physics here is very much involved. So one
Mhm.
thing that Rabbi asked, and it's actually big deal. It's actually big deal in this kind of problem. That means when the dimension of your channels go very low down to nanometer,
Mhm.
there are some peculiar things that might happen.
Mhm.
So for example, your sleep can be changed dramatically.
Yes.
Sometimes you see some stick sleep motion,
Motion. Yes.
and even when you like, I have seen some works where people try to use the CNTs, I mean carbon nanotubes, as
Mhm.
sleeps. Uh, like the fluid particles itself, for some reason they get accelerated through the tube.
Tubes. Yes. Yes.
Right, there are a lot of things that that might not be I mean that you might not be able to capture that sort of physics
Mhm.
with this simplistic model. So what people do in fluid mechanics community, I know you're from heat, you're
Mhm.
analyzing it from heat transfer perspective,
Mhm.
but in fluid mechanics community, they actually write up their own code for this kind of
Mhm.
problem, and especially focusing on the force field that they're
Trying to work. Yes.
trying to
Mhm.
replicate. So okay, so the question that Rabbi asks, that at nanoscale surface, I mean, things might be very different, right? Depending on
Mhm.
what kind of surface. If I'm not wrong, if I'm not interpreting Rabbi's questions in the wrong way,
Mhm.
that if you like modify your surface, it might have an effect on the physics itself. So
Mhm.
I
Yes.
guess if you want to if you guys want to capture that one, maybe it's better to work on the fluid mechanics aspect of the problem, right?
Yes.
Uh,
Right.
if
Yeah.
you
Right.
focus on that one and like try to figure out what kind of physics, what kind of force field, what kind of calculations you guys can make, then I think it might be a better way to deal with it. Another
Yes.
thing,
Thank you.
just
Thank you,
quick,
Lennard.
very
Yeah.
quick note. So in terms of fluid mechanics or moving body type of MD simulations, people do statistical analysis, right?
Right.
Because
Yes.
they are not really solid and they're not staying
Yeah.
at the same place, right? So
Right. Yes.
have you guys made that kind of statistical analysis?
Yeah, we did some sort of radial distribution function, but those things haven't expressed in this paper because there was a paper size limitation. That's why we didn't analyze that part and added those parts here. But we worked with different radial density function, RDF, and showed how the RDF varies when we are going with the phase change transition phenomena like that, how the peak values are changing like that.
Uh,
But we haven't added this in our slides right
no,
now.
what I meant is that even if you start with the same system, since it's a fluid
Okay, yeah.
mechanics system, if you run the same simulation for 100 times, your
Mhm.
data will not be the same. I
Yes,
mean,
the
your
data will
say,
not
for
be same.
example, your
Yes.
temperature trend, it will have a like statistical variation in it, which is very
Yes,
obvious because
yes,
it's not.
yes.
Yeah, I mean, if you could add that part in your later
Okay,
work,
yes,
maybe they
yeah,
will
yeah,
get into better
yes,
journals, right? And
yes,
because
yes.
fluid mechanicians like to see those things in their
These things,
on the
yeah.
before
Yes,
submitting.
yeah, and also so thank you so much for your suggestion. And also, I worked with the Argon right now, but we will certainly go to water for a better interaction and better physical phenomena.
I mean,
Yeah.
Argon is way more difficult than you think it is. I mean, if you open a
Yeah.
physics of fluid journal or like journal of fluid mechanics, you will see most of the papers are dealing with argon. So you don't ignore don't ignore the power of argon and simple surfaces. We still don't know a lot of things there. So yeah, I
Yes.
mean, best of luck for your next work.
Yeah.
Thank you so
Thank
much for
you.
your
Thank you
talk.
so much. Thank you so much. Yeah.
Yeah, as I mentioned, if you have any more question, you can put it in the chat box, or you can unmute yourself and ask the question.
Yeah,
Uh,
so I want to add something. Thank you, very. It was a very nice talk.
Thank you.
And so, like about this slide, I have like I initially had one question, like
Mhm.
why your like phase change or temperature change is enhanced when your like system is hydrophilic. So like I was thinking that I thought like one reason be like this, like you have to distinct behavior, like two distinct regimes, you can say, like one with like hydro weighting factor 0.1 and another like all other, right?
Mm-hmm.
So like I was thinking like when your like weighting factor is 0.1, this means that you have like almost no interaction between the argon and copper, right?
Right, right,
So what can happen is like as the interaction is very low, the heat is transferring very slowly from the copper to the argon.
right.
So and like this argon, like they are almost behaving like they are almost free from the copper. So like it's just the heat transfer is something like you are placing some kind of hot zone in some air and you are measuring it. So it can be something linear, like
Okay,
that's the conduction thing and
okay.
convection thing. And for like when your interaction is higher, what happens is like your interaction is higher, lots of heat can go from copper to the argon.
Mm-hmm.
So initially your heat transfer is like very high. But
Mm-hmm.
if you see in the second figure, like net evaporation number,
Number,
as
yes.
the interaction is higher, like the weighting factor is higher, like
Mm-hmm.
not all argon can leave from the copper surface, right?
Copper surface, right,
So
right.
ultimately, at the end, you can see like lots of argon atoms are still like attached to the copper surface.
Mm-hmm.
So like argons are not moving from the copper surface because their interaction is higher. So
Higher.
that after some time, your like temperature increasing are like not increasing because like not many argons are leaving from the copper
Mm-hmm.
surface.
Copper
That's
surface.
why,
So that's a saturation
yeah. So
point. After a
initially
certain point, yeah.
your temperature rising is like very high. Then as like after some time, like there is almost no heat transfer.
No
So
heat
that's
transfer,
why
yes.
you are seeing low
So
net.
that's basically when you reach to like 3 nanosecond, then that maximum systems are almost at the saturation point. So at
Yeah,
that saturation point, yeah,
yeah, it's
there will
almost like
not be, yeah,
equilibrated.
yeah.
So
So
this
there will
can
be
be a
not,
reason.
yeah, yeah. So this is the region. That's why there is a flat slope you can see here in the net evaporation curve. So that are almost saturated, and there is no a particle moving from the solid surface to the vapor region here. But as for this curve, as the heat transfer is not that much, and so it's like almost at the last point, there is some particles which are certainly moving from the net evaporation number. That's why still this value is increasing. And after like 4.5 nanosecond, it's like kind of constant for hydrophobic condition. Yes. So it reaches to equilibrium at a later point than the hydrophilic surfaces.
Thank you for the
Yes, thank you for your explanation. Yes,
Yeah, I guess that could be an explanation for the linear.
for the linear growth. Yes, for the weighting factor 0.1. Yes,
Right, right.
yes, yes. Thank you, Turash, for your explanation.
Srishti, I have one more question. I actually forgot about
Yes,
the reliability
yes, sure,
concerns.
sure.
Yeah. So I heard in different conferences about like when they actually apply these surfaces in different applications. For example, in power plants, any boiling surfaces, right? When they where they need very enhanced cooling for performances. So the reliability of using these surfaces in a long term is a major concern now, because the hydrophobicity and the hydrophilicity, certainly that characteristic will degrade over time. I understand that you're simulating over like nanoseconds. It's a very like a very confined time frame, I would say.
Time frame, yes.
You have a very good temporal resolution there. But I was wondering, is it possible to generate any understanding at the nanoscale that will lead to understanding the reliability and the degradation of the surfaces in the bulk scale?
Okay, so with time, how hydrophobicity or hydrophilicity is changing with time, right?
Right. Yeah.
In nano level, I think I'm not sure whether in this nanosecond level it will change that much. But yes, yeah, we can check that one, or we can work on that one. So There we won't have to fix the hydrophilicity. We will give it as the initial value, but will not fix it. With time, it might change. So yes, we can check that one, but I'm not sure whether within this time frame or nanosecond or even with millisecond or something, if we go a large time frame, it might change that much. But yeah, thank you for your suggestion. We can definitely check that one in the later works or something like that. Yeah, thank you.
Hello, Srishti. I think it was a nice talk. I just
Yeah, thank
interrupted.
you.
Sorry about that. And I wanted to say that the question that Rabbi asked, that if we can investigate those phenomena for the higher time scale. But I think it's not possible in the nanoscale. You have to go to the mesoscale simulation, especially fluid dynamics simulation for that. And yeah, maybe you can explore on this mesoscale simulation to simulate
Yes.
those these particular phenomena for
Yes.
higher time
Yeah.
scale.
Yeah.
In that
I mean,
case,
Siddhartha,
you will
yeah,
see some kind of change or some kind of real life phenomenon at a very high time scale. You can go to like hours, and yeah, you can go up to hours.
something weird happened.
Did they have a
So-
sound?
Yeah, so Siddhartha,
Sorry.
so I was actually following up with your concern. Yeah.
Yes.
But like what I wanted to ask was, like, is there any phenomena that is happening at nanoscales that can be captured with the nanosecond time frames that can give us some understanding that well, these phenomena can actually lead to the degradation of surfaces in like infinite times, for example, for like 1 hour or 2 hour. So because like physically it all starts at the nanoscale, right? So
Exactly.
yeah, so that's what I was basically wondering. Is there any way, I mean, in physics, I mean, probably there is some analytical calculation or closed form solution to this. People have probably have done this like in a theoretical way. But I was wondering whether it is possible to run some simulations and capture those events at the nanoscales, and we can tell, yeah, this particular event can actually lead to degradation of hydrophilic or hydrophobic surfaces in the long run.
In the long run, yes, exactly. Yeah, thank you for your suggestion. Basically, I didn't see any work like that, but yeah, certainly we can try that one if we can model that type of simulation, which will show the degradation of this hydrophilicity or hydrophobicity in the nanoscale. And that will be a really good work. Yeah, thank you so much for your suggestion. Yeah, I will definitely try to do that. Yeah.
We have a question in the chat box.
Okay.
So Sadip Fardin is asking why there is an upward trend after 3 nanosecond for weighting factor 0.1 in the net evaporation number versus change of evaporation number with time.
Okay.
So
yeah. Thank you so much for your question. So basically, if you see the slope of the curve with hydrophilic, those are very steeper right now. So a lot of liquid are going to the vapor phase here, but the slope with 0.1 is lower. That means not that much liquid is going to the vapor phase. So when it is going like that after 3 nanosecond for hydrophilic surfaces, most of the liquid are in the vapor phase. So there is no liquid, those will go to the vapor phase. That's why the net evaporation number is not changing here. But for hydrophobic surface, as the heat transfer is slow, so it is going slowly to the vapor phase. The liquid is going slowly to the vapor phase. Still after 3 nanosecond, there are some particles in the liquid regime which will go to the vapor phase. And it will go to like equilibrium after nearly 4.5 or even like 5 nanosecond. That's why after 3 nanoseconds, still this graph is increasing, but these graphs are not increasing. They're like at the equilibrium position, or the slope is at the same. Yeah, thank you so much for your question.
there is another question.
Another question. Okay. Yeah.
In temperature versus time graph, initially up to 1 nanosecond for hydrophobic case, temperature is almost constant, which is reasonable, I guess. But for hydrophilic case, temperature is decreasing. What could be the reason for that?
Okay, so yeah, that's another good question. As I have mentioned, we have kept this zone at basically at 0.5 nanosecond. We have tried to keep the surface at 90 Kelvin. That means we are giving heat flow to the surface. That's why the value is slightly enhanced. At 0.5 nanosecond, we stopped giving heat and tried to equilibrate the system at 90 nanoseconds. So that's why initially there might be a higher temperature here, but after 0.5 nanosecond, when we'll stop the thermostat and try to equilibrate the system at 90 Kelvin, that's why it is almost linear to 90 degree. But initially, when we started heating the system, that's why the heat is slightly higher than this zone. So there is two distinct zone here. One zone is before 0.5 nanosecond, one zone is after 0.5 nanosecond. So after 0.5 nanosecond, the temperature is almost equilibrium at 90 Kelvin because we stopped giving heat and tried to equilibrate the system. But before 0.5 nanosecond, we're giving heat to the solid surface. That's why the temperature is slightly higher than this 90 Kelvin. Thank you so much for the question.
Hello again. I have
Yeah.
like one more like observation. Like
Yeah.
I think like if you continue this simulation for slightly longer time, let's say like instead of 5, if you continue the thing for 10 nanosecond, you might see like it can be possible to decreasing the temperature here, like the first figure. So you can look into this because like what
Yes.
happens, you are applying the temperature on the surface, right? So like when these fluids are like they are not getting any heat from the surface when they are evaporated, so they might try to like reduce their temperature, or like
yes,
it can be possible. You can like look into it.
yeah, if we go for a longer time, like as I said, 10 nanosecond, this graph might go a little bit lower direction. Yes, that might be possible because there is no evaporation taking place, so those particles will take it, but and drop the surface temperature a little bit. Yes, that's possible. Yeah, and thank you so much for your suggestion.
Yeah, anybody else has any question or comment, please feel free to pitch in. Okay, looks like we have no more questions. So I would like to thank everyone again. Before ending the meeting, I'd like to ask Vivek about the announcement about our summer meeting. So Vivek, if you can please announce the meeting of our summer, announce the summer meeting. That would be really great. And also, I'd like to thank again Srishti Bhai for this amazing talk and for giving us the opportunity to learn about basics and also some of the applications of empty simulations in heat transfer. It was a very good experience, and I'd like to thank you on behalf of all of us.
Yeah, thank you so much, Nahid. And also, I would like to thank everyone for joining here and have the cooperation here. Thank you so much. Yeah. Hope to see you.
Srishti, can you kindly stop sharing?
Yes.
Both I want to share his screen.
Yeah, first of all, thank you, Srishti, for this wonderful talk. Although it's not my field, so I didn't want to keep in and like ask weird questions. But yeah, it was an interesting talk. So there are two things that I want to talk about. Is one of the things is our next speaker. So our next tentative speaker is Pratana Roy, which is who is a wet grad of 01 batch mechanical engineering. He's now working as a staff scientist at Lawrence Livermore National Lab. We already primarily arranged everything, but we'll see. I hope he will be able to make it on June 1st, like the first week, Saturday of June. The second announcement that we have is the summer meeting. So this summer meeting is a like unofficial thing. Like we know a lot of undergrads are working right now at BUET in different interesting topics, and we want them to like present their stuffs and so that they can get like like construct criticism from us and like suggestions from us, like what we have right now doing it. So they can like, I know most of them don't get to interact with their advisor a lot, and they don't have good directions where they're going. So I would encourage all the undergrads, whatever they're working on, regardless of like it's something big or something small, you should go ahead and submit your proposal, or like it could be proposal, it could be like half done work, it could be very elementary works, or it could be full work. Just submit what you have. We'll look at it and we will try to give like constructive criticism and suggestions and all, definitely whatever you need to move forward with the project. So I would encourage, like, if you know like all the senior members, if you know someone that who is interested, they can also ask them to submit all the works they are doing or have done or planning to do, whatever it is. Yeah, someone wanted to ask a question about the meeting.
Yes.
Yeah, definitely go ahead and ask. Just unmute yourself. Riyad Shafkat, you can unmute yourself and ask the question. It would be great. Everyone can hear it.
My question was, there are topics about heat transfers. Can we present topics on thermodynamics?
Yeah, definitely. I mean, we probably didn't include all the single topics line by line, but yeah, definitely if you have something interesting going on in thermodynamics, yeah, definitely we would encourage it.
Thank you.
Okay, with that, I think we can, if nobody has anything else to discuss, with that, I think we can end our meeting. And again, once again, thank you for coming, taking all your time in this weekend and coming to talk about your research, Srishti Bhai.
Thank you so much. Yeah.